Hey everyone, so today we are talking about titration curves. So titrations are used to help us kind of figure out the concentration of a certain liquid. And it deals with an acid or a base. So in my drawing here, I have a base in the burette here, and I have an acid in this e-flask down here. And the acid could be up here, or the base could be down here. It really doesn't matter. It depends on what we're analyzing. If we're analyzing an acid, it's going to be down here. If we're analyzing a base, it's going to be down here. And the thing on the bottom is going to be called the analyte. It's what we're analyzing. It's what we're trying to figure out what the concentration is. And then the thing in the burette is called the titrant. That's what's doing the titrating. All right? So what we'll have is we'll have this set up here, and we'll have this pH meter in here that's going to record the pH as we add base slowly to this acid. So initially the pH should be low, and then as we add base, the pH should start going up. Well, when we take that data and put it on a graph, it looks like a curve like this, or a titration curve. A titration curve is pH versus volume of our titrant added. So as you can see, we start out with a low pH, which makes sense, and then it starts to level out and slowly increase and then level out again. So today what we're going to be doing is we're going to be looking at these pH curves, going to figure out how to analyze them and how to do some calculations in order to help us solve what we are overall trying to do with the titration, which is find the concentration of that analyte. Okay, so our goal today is to analyze these titration curves, see what they're telling us, and then do a couple calculations with them as well. So here are two titration curves. One you can see starts at the top and goes down, and one starts at the bottom and goes up. And this just depends on what we're analyzing. What is our analyte? Here, our analyte that we start out with has a high pH, so it is a base. So what we're analyzing here is a base. Here, the pH is low. So what we're dealing with here is our analyte, that thing in the bottom flask, is an acid. So you'll see pH curves going from top to bottom or bottom to top, just depending on what we're starting with. Here we're starting with a base. Here we're starting with an acid. The first most important thing that you have to be able to identify is the equivalence point. Okay, the equivalence point. It's just halfway between this downward slope. So the downward slope is somewhere right around here. Okay, if we're looking at this one, the downward slope for this one, if we're going halfway, the equivalence point is going to be right about there. Okay, well, what is the equivalence point? Well, the equivalence point is just when the moles of acid equal the moles of base. All right, it's when the moles of acid equals the moles of base, and that is super important. At this point, we could go ahead and we could figure out what the concentration of our analyte is, which we'll talk about later. All right, and here, same thing. It is moles of acid equals moles of base. And one more thing about these two graphs we got to look at. If your equivalence point is roughly around a pH of 7, like we'll say this one is, that means that we had a strong acid and a strong base mixing together. Okay, if we have a strong acid and a strong base mixing together at their equivalence point, their pH should be 7. So they should cancel each other out and make each other neutral if we add the same amount of moles of each of those guys. So this titration curve is between a strong acid and a strong base. The reason because our equivalence point is at a pH of 7. Those two strong acids and bases neutralized each other out when their moles of acid and moles of base equal each other. Let's move on to this one down here. This one's a little bit different. Here at our equivalence point, we're above a pH of 7, so we got a higher pH there. So when we have moles of acid equaling moles of base, and we have a pH that's higher than 7, that means that our base was stronger. So in this titration curve, we have a strong base mixing with a weak acid. And again, the reason we are able to tell that is because at our equivalence point, our pH is greater than 7. All right, an example where it might look different, where we have a strong acid with a weak base, is just kind of this but shifted downward. So an example where we will have a strong acid and a weak base, let's see here, is going to be something, I'm going to fix this just a little bit, like this, okay? Say our pH is 7 halfway up, but then we look at the equivalence point halfway between that giant slope, it's going to be right there. At the equivalence point, the pH is less than 7, so we could say that this was a strong acid, weak base titration. Alright, so strong acid, weak base titration, the equivalence point is below pH. We have a strong base, weak acid titration when the equivalence point is above our pH is 7. Let's go ahead and identify some more things about this titration curve. So, some other things we need to know about a titration curve is you'll notice that we have this somewhat sort of flat region at the beginning of our titration. As we start to add base, say at the beginning of this titration, this area is very flat. This area right here, let me draw this a little bit more prominent. This flatter region here, before it starts increasing a whole lot, is known as the buffer region. The buffer region. What is a buffer? A buffer just resists changes in pH, and we'll talk more about that later. But that makes sense, right? Because here we're not getting a huge change in pH, so that makes sense that it'd be called the buffer region, since buffers resist change in pH. And the thing we have to know about this buffer region is that halfway in between this buffer region, our pH is going to equal our pKa. pH will equal pKa. Well, what is pKa? It is just another way to measure the strength of an acid. Over here you can see I put our pH scale. A low pH is acidic. High pH is basic. It's the same with pKa. A low pKa is acidic, a high pKa is basic. The only difference is the scale. pH goes from 1 to 14. It could even go beyond that. But a pKa can range from -8 to 50. And the good thing to know about this is pK is just kind of a nicer way of writing Ka. You'll note that negative log of H plus equals pH. You know, it's kind of a pain to write out H plus as a strength for an acid, right? If I say 1.8 times 10 to the -5th concentration of acid, you don't know how strong that is. But if I say a pH of 2, you know that that's a stronger acid. It's kind of the same with pKa. If I give you a Ka and I say it's 1 times 10 to the -7th, you know, that's a weakish acid. Or if I say 1.8 times 10 to the 7th, you know, that's a strongish acid. But that's why they do something like pKa. If you just take the negative log of Ka, you will get pKa. Alright, so again, it's just a way of simplifying it. You know, if I say 2 on the pH scale, you know that's strong. If I say 1.8 times 10 to the 3rd of H plus, you're not really sure if that's strong or not. So it's just a way of simplifying, you know, a strong Ka. So again, similar, you just negative log it to get pKa. Alright? And so a question I might ask you is, what is the pKa, or what is the Ka of our analyte that we're analyzing, the acid? And you might say, well, I don't know, but what I can do is I can look at this titration curve, I can find the halfway of the buffer region, and we could say, that's somewhere around 2.5. So you could say that the pKa is equal to 2.5 of the acid. solution. And then from there, you could go ahead and calculate Ka, right? Because we could take 10 to the negative pKa to get us Ka. That is something they like to throw at you. They like you to be able to know that halfway between the buffer region is where pH equals pKa, and we could figure out the pKa and the Ka of our analyte, or the thing that's in the beaker at the bottom of our titration. Let's go ahead and let's do one more thing where we have to analyze a titration curve. So before I move on with this, the one thing I wanted to note is that this halfway between the buffer region that I was talking about earlier is called the half equivalence point. Half equivalence point. And the way we find that is we just go from start to our equivalence point, and then halfway between there, we draw a line, and that is our half equivalence point. So that's the accurate way in order to find our half equivalence point. Is just go from start to middle, find halfway down, and then that's our half equivalence point. Another thing you could do is that, say at the equivalence point, our volume was 20 milliliters. Well, what you could do is you could just find the 10 milliliter volume, go up, and that will also be your half equivalence point. So let's go ahead and let's look at this and see what's happening now at a molecular level. So this is just a titration where we have NaOH as our titrant and HCl as our analyte. So at the beginning, we just have a bunch of HCl. I have my key over here, H plus, Cl minus, Na plus, and NaOH. So from the start, we just have some HCl molecules. In real acid terms, these are going to dissociate into H plus and Cl minus, but I have put them together just for simplicity sake. Okay, so yes, you'll probably be seeing these and you'll be like, Mr. Dahmer, this is a strong acid, these should be dissociated. They are. I'm just writing them like this so that it's most simplistic. So at the beginning, before we add any NaOH, we just have some HCl chilling in our flask. Well then, as we start to add NaOH, that NaOH is going to start to eat away at that H plus and that HCl. So that OH is going to come in here, it's going to take away that H plus, and then it's just going to leave us with that Cl minus left over. And then this guy is our Na plus, right? That OH minus and that H plus react together to make water, so that Na plus is left on its own, and that Cl minus is left on its own. So at this 2 point in our titration curve, we like to say that HCl equals Cl minus. So at the half equivalence point, at part number 2 here, HCl equals Cl minus, which we see right here. Our HCl, we have the same amount of Cl minus. Anything to the left of this half equivalence point, we have more HCl, and anything to the right of the half equivalence point, we have more Cl minus. They like to ask you that as well in the AP exam. We'll probably put a point in here, and they'll say at point A, is there more HCl or is there more Cl minus? Well, you know everything to the left of the half equivalence point, there's more HCl. Okay? At the half equivalence point, the HCl and the Cl are the same. And then anything past that half equivalence point, you're going to have more Cl minus. As we move forward and we get to our half equivalence point, right, that's where the moles of the acid and the moles of the base should be equal. So as we see here, the moles of the acid, the moles of the base have all reacted together and made water, and we're just left with our remaining ions, our spectator ions, right, of Cl minus and Na plus that equal each other. That means we had to have had the same amount of H plus and the same amount of OH minus in there. So at the equivalence point, you see that there. And then as we continue forward, we keep continuing adding NaOH, and then those NaOHs have nothing to react with, so they're just chilling as full molecules together. They're not reacting with anything. They're like, hey, where'd the party go? And there's no H pluses there, right? Now, like if you do a titration problem and you get confused, you could say, what in titration? Right? Get it? Okay, whatever. Lame joke for the day. I had to throw it in there. I had to. So anyway, that is what's happening at a molecular level and a titration curve. Be aware of that half equivalence point. Be aware that the acid and the Cl minus are going to be equal to one another. You know, if it's HBr, it's going to be HBr is equal to Br minus. If it's acetic acid, it's going to be acetic acid equal to ethanoate at that half equivalence point. Everything to the left, we have more HCl. Everything to the right, we have more of that Cl minus. All right, so that's what's happening there. So let's go ahead and now let's move into some calculations with these titration curves. Okay, everybody, here is a titration curve, and I got a lot of parts in here because I want to cover as much as I possibly can. Okay, so part A, it says what strength of acid base is in this titration. So by asking that, I'm asking, is this a strong acid, strong base combination? Is this a strong acid, weak base combination? Is this a weak base, strong acid combination? Did I just say that twice? Oh well, you know what I mean. So anyway, we're looking at this, and one thing we could do is we could just look at part B and look at what we're combining here. We got nitric acid and NaOH, that's strong acid, strong base combination. But what else you can do is we could look at this half equivalence point here, roughly about right there. Yeah, about halfway between this steep curve, I'd say probably right there. And we could bring it over, and it's at a pH of about 7. So that tells me it's a strong acid, strong base combination. If it was above 7, it'd be a strong base, weak acid combination. If it was below 7 at the equivalence point, it would be a strong acid, weak base combination. So, part B. 50 milliliters of nitric acid is titrated with 0.20 molar NaOH. What is the initial concentration of the acid? So I like to just draw a picture just to kind of tell me or remind me what's going on here. So I got this nice little picture here. I am titrating an acid, 50 milliliters of acid. So that means that this down here is our acid, and this up here is our base. We're titrating it with NaOH. It looks like we got 50 milliliters of this down here. I'm just going to write 15 milliliters down there. And I need to figure out what the concentration is. Well, I got the volume, right? Concentration is moles over liters. I have liters. I just need the moles. And that's kind of the problem here. I don't know the moles of acid, but what I do have is my nice concentration curve. And with problems like these, what you're going to be looking at is the equivalence point. That is our main dude right there, our equivalence point. Remember, at the equivalence point, moles of acid equals moles of base. So at this point, if I could figure out the moles of the base, I could figure out the moles of the acid, right? But here's the thing, what do I have about base? I have the molarity, right? Okay, so I have the molarity, right? Molarity equals moles over liters. I got that part. But do I have the volume? Yeah, right? It's down here. That's what this is. Down here at the bottom is volume added. So what I do is I go to the equivalence point, I go down, and let's say it's 40. Okay? So the volume added to get to that equivalence point was 40. So now I have molarity of the base from here. I have volume of the base from down here on my graph. So let's go ahead and figure out moles of the base now. So what I'm going to do is I'm just going to take volume times molarity. Remember that volume has to be in liters. So I'm going to take that 0.20 molarity. I'm going to times it by 0.04 liters. Okay, 0.04 liters, and that's going to tell me that 0.2 times 0.04, that's going to tell me that I have 0.008 moles of NaOH. Okay, 0.008 moles of NaOH. Let me make sure that's right. 0.2 times 0.04. 1, 2, 3. Yep, we're good. 0.008 moles of base. Well, remember at the equivalence point, moles of base equals moles of acid. So this is moles of base. Guess what? I have that same amount of acid. Okay? Same amount of acid. So, again, I want the initial concentration of the acid. That's right at the beginning. I have the moles that were in that acid. Now I just got to divide it by its volume. in liters, which initially was 50 milliliters, which is 0.05 liters. Let's take 0.008 divided by 0.05. So the concentration of that initial HNO3 was 0.16 molarity. Okay, I took care of A, I took care of B. So remember, whenever I ask you for the concentration of the acid, remember we use the equivalence point. I could also ask you for concentration of the base if the base is the analyte, okay? If we have a reverse titration curve, same deal, okay? C, calculate Ka of the acid. You're thinking, okay, Ka, that's products over reactants, but I have an initial concentration of the acid, but I don't really have an X or anything like that. I don't have a Ka to help me find the X. I'm looking for Ka. They didn't give me a pH. So just use our handy dandy friend, the half equivalence point, right? Remember, the half equivalence point, pH equals pKa. Well, if we have pKa, we could go ahead and we could find Ka. So I'm going to go ahead and erase this. We know the concentration. I'll leave that there. So let's find the half equivalence point. That's the equivalence point. It's also at 40 milliliters. So let's go that 40 milliliters was to reach the equivalence point. So at 20 milliliters, I will hit the half equivalence point. Okay, so there's my half equivalence point. I'm going to bring that line straight over to figure out what the pH or the pKa is. Well, at the half equivalence point, the pH equals the pKa. The pH is 3, so that must mean that my pKa equals 3. Okay, so the pKa of that acid was 3. Well, remember that if we take 10 to the negative pKa, we should get Ka. So let's go ahead and let's do that. Let's take 10 to the negative 3, and our Ka is 0.001. So we have gone ahead and solved part C. So remember, if they asked for pKa, you could get it from here, and if they asked for Ka, you could also get it from here as well, the half equivalence point. All right. And then part D, it says at point A, which is right here, which is more prevalent, HNO3 or NO3 minus? Remember at the beginning, all we have is a bunch of nitric acid, a bunch of HNO3. Once we hit the half equivalence point, the HNO3 and the NO3 are equal. And then once we get past there, the NO3 is more prevalent because we're eating up a lot of that H+, that NO3 is being left to fend for itself. So our answer is NO3 minus. Whenever we get past that half equivalence point, we get more A. Right? Let's do one more, and then we can be done with titration curves. Last example, everybody. So, again, you can see our titration curve is inverse. So here we actually start at a high pH. So we're starting with something a little bit more basic at the beginning. Keep that in mind as we're going through this problem. So we're going through this, and it says, what strength of acid-base are added? So strong acid-weak base combination, strong acid-strong base combination. Let's go ahead and let's look at our equivalence point for this. So I take halfway in between this straight line, and I get about in the middle here. I come over, and I get below a pH of 7. So we're dealing with a more acidic solution here. So if it was at 7, we'd say strong acid, strong base, but since it's below 7, we're going to say it is a strong acid, weak base combination. Again, because at that equivalence point, the pH is below 7. And then if we look at part B, we're dealing with NH3, which is typically a weak base, and HCl, which is a strong acid. So that makes sense. Part B, we have 25 milliliters of NH3 are titrated with 0.05 molar HCl. Find the initial concentration, not of HCN, of NH3. Okay, NH3. So what we're going to do is we're going to go ahead and draw a little picture here, right? It says NH3 is titrated, so that's going to be at the bottom. HCl is going to be at the top. I want the concentration of NH3, so I'm going to need moles over liters. They gave me milliliters, which I could change to liters, but I need moles. Well, remember, at the equivalence point, moles of acid equals moles of base. So if we could figure out the moles of acid at the equivalence point, we could figure out the moles of base at the equivalence point as well. So let's go ahead and let's do that. I know my molarity of acid is 0.05. Moles, I don't know. That's what I'm going to find. But volume. Let's look at the equivalence point. And I'm going to go straight down. And that looks somewhere around, I don't know, 37-ish. Okay, so I used 37 milliliters of HCl before all the moles got ate up. So that's going to be somewhere around 0.037 liters. 0.037 liters. So let's go ahead and let's multiply those together to get moles of our acid. 0.00185. 0.00185 moles of my strong acid HCl, which remember is my equal to my moles of base. So in this case, we also have 0.00185 moles of NH3. Cool. So now we have moles of NH3. We have volume of NH3. So now we can figure out the concentration. I'm going to get rid of my picture here so I can finish my calculation down here. I have 0.00185 moles of NH3 over our initial volume of 0.025 liters. And that will give me a concentration of 0.074 molar NH3. So part A is done. Part B is done. Here it says find KB. And this is why I brought this up and I did a reverse of this, okay? Remember that when it's going down and upward, the half equivalence point is pH equals pKa. Well, when we're dealing with this downward sloping one, the half equivalence point is POH equals pKb. Okay, so at the half equivalence point, if we're dealing with a base, the POH is equal to pKb. I've never seen a problem like this on the AP exam because it's kind of confusing, but I just wanted to bring it up to you just in case. Okay, so here is the thing. So the problem is, okay, POH equals pKb, but remember we are at a pH scale. So we're going to have to do a little finagling here in order to get this to work. So again, why am I finding KB or finding pKb? Remember, if we could find pKb, we just take 10 to the negative pKb to get KB. So let's go ahead and let's get started. So we know at the half equivalence point, okay, our POH equals pKb because it's the reverse of a strong acid to base, or acid to base titration curve. We'll bring that over, and it's about pH of 9.5. So we have a pH of 9.5, but again, pH isn't going to help us because we're dealing with a base. We need POH. So remember 14 minus our pH equals our POH, which is going to be 4.5. So our POH at the half equivalence point is 4.5. Well, luckily that's also the same as our pKb. But I don't want pKb, I want Kb. Well, luckily there's a nice little equation for that. 10 to the negative pKb, equals Kb. So I'm just going to take 10 to the negative 4.5 to get Kb. 10 to the negative 4.5 is 3.616, times 10 to the negative fifth. So that is my Kb. 3.16 times 10 to the negative fifth. Next, it wants more HCN. Again, not HCN, more, sorry guys, more NH3, or in this case NH3 or NH4 plus at point A. Point A is right here. Remember, we are starting with NH3 at the beginning. When we reach the half equivalence point, some of that H plus has eaten up that OH minus, leaving us with NH4 plus. So remember, at point A, we're going to have more of what we started with, which in this case is NH3, right? So we add H plus, that H goes in there, gets eaten up by that base, and gets turned to NH4 plus. So NH3, more NH3, at the half equivalence point, NH3 and NH4 plus equal one another. Past the half equivalence point, we get more NH4 plus. Please, if you have questions over these titration curves, please reach out. It takes a while to get used to them. There's a lot of stuff here, right? You got equivalence point, you got half equivalence point, you got calculations, you got strong acid versus weak acid. But hopefully, through practice, we could get used to all of that stuff. So please reach out if you have questions. That's it. Have yourself a great day. Let me know if you have any questions.